We now consider finding the volumes of solids that are not solids of revolution. That means that we don't have cross-sections that are perfectly circular. For example, the cross-section can be a square, can be a rectangle, can be a triangle, can be an isosceles triangle, an equilateral triangle, could be anything. So volumes by slicing, consider a solid that lies between a plane perpendicular to the x-axis at x equals a and a plane perpendicular to the x-axis at x equals b, and assume that the plane perpendicular to the x-axis at a typical x value has a cross-sectional slice given by a of x. And the key concept is that the cross-sectional slice has to be perpendicular to the direction in which you will integrate the slice. So the volume of the solid is the integral of the cross-sectional area. So that means that the volume is the integral from a to b, a of x dx. Cross-sectional slice is perpendicular to the x-axis, so we integrate in the x direction from a to b. All right, so the question here is a solid's base is a circle of radius 1 in the xy plane. Cross-sections perpendicular to the x-axis are squares. Find the volume of the solid. Let me see if I can draw a small picture here. So basically we have a circle of radius 1 and cross-sections perpendicular to the x-axis are squares. So you can see it's coming out of the screen like that. All right, so the first step, as always, is to draw a picture of the cross-sectional slice and a region in xy plane that describes the solid. The second step is to find a formula for the cross-sectional slice perpendicular to the x-axis, such as a of x. And the third step is to integrate the area slice a of x to find the volume of the solid. So the volume is the integral from a to b, a of x dx. And key concept is that the cross-sectional slice is perpendicular to the x-axis, so we add up these slices in the x direction to find the volume of the solid. All right, so the next step is to draw a picture of the base and the area slice. As we saw in the question, we have a base, a solid's base that is a circle of radius 1 in the xy plane. Cross-sections perpendicular to the x-axis are squares. So here's what we have. We have the cross-sections perpendicular to the x-axis given by the red line segment. That's the base of the square. Let me see if I can draw this in 3 dimensions just to give an idea of what this looks like in 3D. So basically it's coming out of the page like so. And these squares are coming out of the page, and the integral basically adds them all up. The biggest square, the biggest cross-sectional slice is actually on the y-axis. And they get progressively smaller, the areas get progressively smaller as x increases from 0 to 1 and as x decreases from 0 to negative 1. So there it is. Here are some of the cross-sections. And we're going to find the cross-sectional slice as a function of x, then add them up in the x direction. These are the slices here, and the integral will add them up. All right, and we have the square here. We have the square is the segment AB has a length 2 root 1 minus x squared. So let's formalize that. Point B has y coordinate equal to root of 1 minus x squared. For a typical x between 1 and negative 1. Point A has y coordinate, which is the bottom half of the unit circle, minus root of 1 minus x squared. For a typical x value between 1 and negative 1. So AB, this line segment AB, has a length root of 1 minus x squared, the top y value minus the bottom y value, minus root of 1 minus x squared, and that's equal to 2 root 1 minus x squared. This is the length of AB, and we have a square, so we just basically multiply it by itself and get the cross-sectional area of the square slice. All right, so we want to find a formula for a of x. Since the area slice perpendicular to the x-axis are square and the length of AB, so AB has a length to be 2 root 1 minus x squared, then the height of the area slice, the height, is equal to, it's the same, because it's a square, 2 root 1 minus x squared. And since the area slice is perpendicular to the x-axis or squares, the cross-sectional slice, a of x, is equal to the length of the base times the height. And they're both equal to each other because it's a square, times 2 root 1 minus x squared. And if we simplify this, we're going to get 4 times 1 minus x squared. And this is in fact the area of the slice here. This area here of this square cross-section is 4 times 1 minus x squared. All right, now that we have determined the area slice a of x, this will form the integrand of the volume. So the volume formula is volume is integral a to b, a of x dx, where the cross-sectional slices are squares, perpendicular to the x-axis. The integral adds them all up. A equals -1, the lower x value of integration, and b is equal to 1, the upper x value of integration. And a of x, the cross-sectional slice, has area of 4 times 1 minus x squared. All right, the next step is to integrate the area slice a of x to find the volume. So volume is integral a to b, a of x dx, where a equals -1, b equals 1, and a of x is equal to 4 times 1 minus x squared. So volume is integral from -1 to 1, 4 times 1 minus x squared dx. So now we can use symmetry here. 4 times 1 minus x squared is the integrand, and this integrand is an even function, is symmetric about the y-axis. So we can just take 2 times the integral from 0 to 1, 4 times 1 minus x squared dx, applying symmetry. 2 times 4 is 8. 4 is a constant, passes through the integral, gets multiplied by the 2. The volume is equal to 8. Integral 0 to 1, 1 minus x squared dx. This is equal to 8 times integral 1. What is the antiderivative of 1? That's just x, because derivative of x is 1. What is the antiderivative of x squared? That's going to be x cubed divided by 3, evaluated from 0 to 1. So volume is equal to 8 times, plug the upper limit in, we get 1 minus 1/3, minus, put the lower limit in, we get 0 minus 0. That gives us 8 times 1 minus 1/3 is 2/3. That's equal to 16 over 3. This is the volume of the solid, where the cross sections are squares. Let's go back to the picture to get an idea of what this volume represents. So basically, we added up all these cross-sectional areas of these square cross-sections perpendicular to the x-axis that are coming out of the screen, and the volume of the solid came out to be 16 over 3. All right, thanks.